This question is a bit of circular motion and mechanics. So just bringing in the formula sheet, the circular motion section, we've got omega, the angular speed, is equal to instantaneous velocity over r. And then we've got centripetal acceleration is given as well. So we've got some relationships here. What we've got in the question is a number of revolutions per minute, which I can easily convert into a frequency, and then I'm going to have to convert it into an angular velocity because I'm not given the angular speed for it. So I've got to do a little bit of work first before I can then solve this. So a little bit of understanding of circular motion, and then there's quite an important step about the mechanics of this. Okay, so looking at the question, we're going to use F equals ma. F equals ma is true no matter what the circumstances. F, remember, is the resultant force, which we're going to talk about in a second. That A is equal to omega squared r. So that's our starting point. So the force required to make a mass accelerate is this. The force required to make a mass m move at an angular speed of omega in a circle of radius r is given by this. So we're going to be using that in a moment. So I can use the revolutions. So we're given revolutions per minute. And I can use this to find the frequency. And from that, I'll be able to find the angular speed. 120 revolutions per minute. It's going to do 60 times fewer revolutions in a second than it does in a minute. And that gives me a frequency, lowercase f, a frequency of 2 hertz. If I know the frequency, I can work out the angular speed. And the angular speed is given by 2 pi f. And that's because the angular speed is how many radians does it go through per second. The frequency tells me how many full cycles it does in a second, and one full cycle is 2 pi radian. So 2 pi radian multiplied by the frequency will tell me how many radians it goes through per second. That will give me 4 pi, and I might leave it at 4 pi. That's around about 12 and a bit, but I might leave it as 4 pi just for simplicity, because I'm going to use that value in a further calculation. So then we get F is m omega squared r, and I know all the values. So I'm going to be able to find the resultant force that's required to keep this object moving in the circle as described in the question. So then the object has a mass of 0.4, 4 pi all squared multiplied 0.45. Calculate that on my calculator, and I get 35.5 newtons. But that is the resultant force. That is the resultant force. And if you look, this is where the mechanics bit comes in. If you look at what's happening in the diagram, you've got mg, you've got tension, and then you must have a resultant force acting towards the center of the circle. So the resultant force that we've just found, which I've done in red, must act towards the center of the circle. And that resultant force must be due to T take away mg. So that resultant force is T take away mg. So the tension, so the resultant force, as I just said, is T take away mg. Therefore, the tension is the resultant force plus mg. So it's 35.5 plus 0.5 times 10-ish. So we get around about 40.5 newtons. Okay, so we're looking for 40.5 newtons in the answers. Now, you can see in the answers, they've given you an option for missing off that you've got to include the weight. So that's a trap. Then if you do the calculation the wrong way, so if you subtract mg rather than adding it on, the 31 option is there as well. So there are a number of things to catch you out with that one. So I think that's a difficult 1 mark question.